Hey everybody, we are here in cyberspace today with Sara Seager, an astrophysicist from MIT who searches the universe for Earth-like planets. We could start out by just having you introduce yourself.
Okay, I can do that. Let me think for a second. Hi, I'm Professor Sara Seager. I work at MIT, the Massachusetts Institute of Technology. Here I'm a professor in planetary science and in physics. And my whole goal is to find another planet that is just like Earth.
So Sara, what is exoplanet research, and why should young people, teachers, and also adults be interested in it?
Well, an exoplanet is a planet that orbits a star other than the sun. So every star in the sky is the sun, and so if our sun has planets, Mercury, Venus, Earth, Mars, etc., it should seem natural that other stars, other suns have planets also. But only in about the last 10 or 20 years, let's say the last 20 years, astronomers have actually been able to find these other planets. But actually, the real reason why it's so cool is because someday, one of the kids today, or one of you, is going to find out how we can travel to another world, far away. It may not be us physically getting in the spacecraft and traveling far away, but somehow maybe our DNA and raw biological materials, I don't know what it is, it hasn't been invented yet. But those other planets are out there to explore, either in our generation using remote space telescopes, or for children today, they can figure out the next step.
So cool.
That's awesome.
It's so cool. So, what inspired you when you were a child to do this kind of research?
I would say that for me, I did not have a set goal that I was going to go into research. I didn't know any scientists. I didn't even know that being a scientist was a job, actually. And in my case, I just remember as a small child seeing the moon for the first time through a telescope. Have any of you seen the moon through a telescope? It's just breathtaking. Like, who would have known that, like, those, what you see when you look at the moon, but in detail when you look through a telescope, it's so amazing. Craters, and you can even see a crater within a crater. It was so amazing to me, I just didn't know about it. And as I went through education and school, I didn't know you could be a scientist for a job, but I eventually learned about that and decided to pursue it.
So you've worked on countless projects. What are some of the most exciting ones?
Well, in some ways, the exciting project is always the current project or the next project, because it's not really finished yet. But I'd say in some ways, my most exciting one, let me think. I'm gonna think of this for a second. One of my most exciting moments was with my then best friend, Gabriella, and we were working on a project that involved transit light curves. When a planet goes in front of the starlight drops by a tiny amount. And if you monitor a star's brightness as a function of time, you measure that curve. Well, what we found was that there are, depending on how you write it, 4 or 5 equations that describe that light curve in terms of things that you can measure, like the drop in brightness, the start time, the end time, and things like that. And if we write all of those equations down and solve them, there are actually 4 unknowns that you'd like to know, like the planet size compared to the semi-major axis, and a few other things. It turns out it's this crazy thing, but we're working through the equations, which get quite complicated because they involve trigonometry to describe things, and we're working through. We knew there was something here because we believed there was a unique solution. Remember, 4 equations, 4 unknowns. We keep working, and all of a sudden, voila, we come up with m over r cubed, which is density, mass divided by volume. Remember, for a sphere, 4 over a third pi r cubed, volume of the sphere. This was so exciting that, from the planet transit light curve alone, you can actually extract the density of the star. How is this even possible? You know why it's possible? Because it turns out that using Kepler's law, it helps tell you if the planet's orbiting the star based on the period. It helps tell you something about the mass enclosed relative to the semi-major axis. And you divide them out, you get rid of the semi-major axis, and what falls out is the mass of the star compared to the volume of the star. And it was this crazy discovery, because when you're in school, your homework's the professor at least, knows the answer to the homework, or the teacher knows the answer, but in this case there was no answer. It's like, here's a problem we thought of. We didn't even know what the answer was. We just had a feeling there was some kind of utility to writing down the math to describe the transit light curve, and that because there were 4 equations and 4 unknowns, there was a unique solution to things we cared about. And this was so exciting because it was like a discovery just using essentially what is advanced high school or first year college math.
So when you find your candidate, how do you go about telling the world?
I think we'd want to wait till we know what it is. So for example, I imagine the future when we launch a starshade, a that flies with a telescope. We block out the starlight and we see the planet. You know what we're going to see first is like a tiny little blob. We call it a blob. Now, is that blob a background star, maybe a background galaxy, perhaps? We know that the Hubble Deep Field showed that even a tiny patch of dark sky has tons of galaxies. What if it's an object that's right at the limits of what our telescope can handle, so it could see there's a blob, but it can't tell anything else? Like look at the atmosphere and see if it's a giant planet or a terrestrial-like planet. So then we might have to be more clever now. What are we going to do? Devote 3 months of telescope time to this object? Or maybe we even need to build a new space telescope. So I just want you to have that thought of discovery process in your mind that we have to kind of iterate on. It's like peeling away the layers of an onion until we can get to the core. So it could be a long time in between when we have this candidate we're really excited about. We probably wouldn't tell the public at that point, but we'd wait and get more data and figure out what's going on.
You mentioned a star shape. What exactly?
Well, what the star shade is a very specially shaped screen, a giant screen, 30 meters in diameter. And it would fly in space together with the space telescope. But that star shade and telescope would be separated by tens of thousands of kilometers. And what the star shade's job is exactly what it sounds. It's shade out a star. It's supposed to block out a star so that we'd be able to see the planet light directly. Because the problem with a planet like Earth that we're looking for is not that it's fainter than the faintest galaxies ever observed by Hubble Space Telescope. The problem is that that faint planet is right next to a bright star. And our sun, get this, is 10 billion times brighter than our planet Earth. 10 billion. And so it's so bright that no matter how you can take that measurement with any reasonably sized telescope, the star light overwhelms any planet signal. And so we need a way to block out starlight, and there's an entire field of optical engineering now, starlight suppression. There's many different ways to get rid of the starlight, but my favorite way is the star shade. And if you wait right here, I'm going to bring you a 1% scale star shade. This,
Oh my god, it's so cool.
and it has been used in desert testing, where the star shade would be at one point, and an LED fake star and planet would be 1 kilometer away, and 1 kilometer in the other direction would be a camera. They do this in the desert at night, out in Nevada. Steps. It's extremely sharp, and this is actually the real shape. What they also do in the testing is they make like damage. They try to make a damaged star shape, and then see that their mathematical model equals what they actually observe. So we're trying to make sure we know what we're doing with the math. So that's the star shape. And if you look behind me, do you want to take a guess what that is on the wall on display?
It looks like
It's one of the pins of the star shade.
It's one of the petals. We call it a petals. Yep, it's one of the petals of the star shade. It's one of these. And this star shade is 1% scale. The one on the wall is 2/3 scale, where it could be considered 100% depending on the actual star shade design.
that's so cool. Oh my god.
There's an animation you can link to, and it shows an animation of how the petals would unfurl from a stone position, and how an inner truss would expand, with the petals snapping into place.
Yeah,
And
I saw that
One
animation.
of the ways that the star shade is sewed and deployed actually has heritage from large radio deployables. There weren't petals on those, but the way that it folds together and then expands is actually something you can look at.
I also saw the video of the TESS spacecraft. Can you talk a little bit about your involvement in that project?
Sure, I could. TESS is an MIT-led NASA mission. It's called Transiting Exoplanet Survey Satellite, and it will come well before the star shade. In fact, TESS is supposed to launch in summer to fall of 2017. And what TESS is, it's an all-sky survey, looking around the entire sky, looking for transiting planets that go in front of their star as seen from the telescope. And there are 4 cameras, and together they take an image on the sky that's huge. It's 24 degrees by 90 degrees. So that's like one strip on the hemisphere. You'll see it in the movie. And TESS will look at each strip for about a month, and it'll cover in 24 months, 2 years. 1 year, one hemisphere, like let's say it's maybe the north. The next, they're not sure of the order yet, then next year it'll be the south. And it'll look for transiting planets, small planets, transiting small stars. And in that 1 month to 2 month period that they have access to, the planets that transit small stars would be in the habitable zone, the so-called Goldilocks zone, not too hot, not too cold, but just right for life, as planets with thin atmospheres heated by the star. And so my involvement in tests is I'm one of this called co-investigator. One thing you should know is that all the test data will be public as soon as possible, actually. Which might be like 4 months from when it was taken, because it can take a while for data quality to make sure the data is calibrated and just ready for the public's use, because the real data, the raw data that the spacecraft takes, is not really the right product that you want people to be using, because there's a lot of things that the people working on the team can fix for you first. The data will be public right away.
That's great. So, how old are your children, and what do they think about what you do?
So my children are age 10 and 12, which is a really exciting age, because the 12-year-old, like, he's old enough to be mini adult, basically. But they're just normal kids, like in the summertime. They don't really do anything too academic. I just let them be kids, and I think it's really important for all parents and students today to not overschedule. I mean, you would not believe the number of kids I see where they don't know what to do when they have free time, because all their time is like with this lesson and that lesson and this team and that team. And it's not producing the type of scientists that we actually want to see, because if everyone's always telling you what to do, you have no way to figure out what to do on your own time, whether it's reading a book, staring into space doing nothing, or just figuring out some kind of puzzle. They also learn how to program. I love that now. I'm guessing that you know how to program, but the thing is, they have this thing now called the Hour of Code. They've made it really accessible, so you can move blocks of code around. And yeah, the Hour of Code. If you haven't seen it, you have to try it, because they want Hour of Code. They want everyone in the world to try coding, but it leads to types of codes for children. And in particular, I hope you can link to a link called Eyes on Exoplanets. It's a really cool piece of software made by NASA, and what you can do with it is download it, and you can click on different stars. It has a real map of the stars that we would see in the sky, and you can find any location on Earth, see what it would look like that night. But when you click on the highlighted stars, it will tell you about what type of planet is orbiting that star.
What advice would you give young people and even older people that want to get involved in astrophysics and space exploration?
Well, I'd say to start out by educating yourself. As you said, anyone with a computer has a whole bunch of tools to look for. There's some really great websites that have up-to-date news and discovery information, and also programs like the one I mentioned, Eyes on Exoplanets. I'd say the next level actually would be to take an online class, whether it's one that you need to get credit for or just, watching it. I know there's a few of them out there on exoplanets and astrophysics and astronomy and other things. And so I'd recommend doing that. The next level is to try to get involved with the citizen science program. There are a few of them where you can help discover a new planet. And this would be by looking at data and clicking on a menu of options of what you think you see. And I think those also have discussion boards, so you can then network with other like-minded people. And often the people who are moderating it are scientists and professionals who then you can get more information that way. If you're a real enthusiast and want to get more involved, that's way harder. But if you're at a university or at a high school where you have a university in your hometown, you could actually try to get an internship there. And that some universities have programs where they welcome high school students and try to slot you into the right one. I did one of those myself, which is why I'm not a biologist now, because I got to try biology, decided it wasn't for me. So you can try to get involved in an internship that way. And so those are the 3 or 4 main ways I'd suggest to start moving forward.
Do you have a favorite sci-fi movie or sci-fi book?
The books that I liked the most actually were Robert Heinlein. He wrote these books in a very engaging way, and many of them actually are written for I think young people, like teenagers. So they're really easy to read, that's the good part about them. And they're often quite short, so you can kind of get through it. But he explored all the cool topics like special relativity, how one twin can go away and come back at the other one's age, time travel stories. And when he wrote these books, I believe they were in the 50s and 60s primarily, it was amazing the stuff he predicted, some of them came true, like ATM, others didn't, like robot servants, but we may be getting there. At least I have this robot vacuum cleaner, although it's just a round disc, it's not a robotic humanoid. And they're just so well written, and I just love the way he took physics and engineering and made a really cool story out of them. So Robert Heinlein was definitely my favorite.
So tell us why you are excited for Exoplanet's.
Actually, I have a model of Exoplanet's out. I'm not sure if you can see it, it's sitting behind me. We'll grab it.
Okay, perfect. I was thinking it was that, but I was like, I'm not sure of that.
So what is this?
what ExoPlanetSat is essentially a tiny space telescope. This would actually go up into space, and this bottom part is a reaction wheel unit. It has 3 wheels that help point this thing in the direction. There's no fuel on board. And it will point at a star looking for a transiting planet. CubeSats are now a revolution in space engineering. And actually, people all over the world now, nations like Ecuador, Vietnam, Estonia, that previously were not spacefaring nations, have now all launched a CubeSat. And it's really a great way to get into space. It's so expensive because anything in space we always like to say it's like 100 times more than it costs to do something on the ground, because it goes there and you can't touch it again. You have to communicate, it has to work basically on your first try. So actually it's a great way for people in engineering schools to actually build something that they can launch.
There's so many planets out there, like literally billions of billions. Can you talk about the Fermi Paradox?
Okay. Well, the Fermi Paradox is that if there are so many planets out there, billions and billions, some of them must have life, and some fraction of those that have life must have intelligent life, and some fraction with intelligent life must have life that can travel in spaceships to come to Earth. And so the Fermi Paradox is, where are they? Why haven't they come here yet if they're out there? And what's great about exoplanets is we can start to help answer that question concretely by just simply saying how many planets are out there that are Earth-sized and Earth-like orbits. And in the future, if we can look for signs of life and infer that there's microbial life on some of the planets, then we can also help to answer the Fermi Paradox by establishing whether or not life is common. Life of any kind, intelligent or not, is common. I do have this sort of weird thing for the Fermi Paradox because I haven't heard this answer too often. What if the aliens just don't want to contact us? It's like, what if we, to aliens, are like ants are to us? Like, would you want to talk to the ants? I mean, it seems like, why would you? And if you did, how would you? So I don't know. I think that's my favorite explanation, actually. It's just my favorite way of thinking about it. Just maybe they just don't want to be bothered.
Do you have a position on whether you think there's extraterrestrial life?
Yeah, I mean, I feel like there has to be intelligent life somewhere. We just talked about it. There's billions of stars in our galaxy. There's hundreds of billions of galaxies, and hundreds of billions times hundreds of billions. I mean, that's like one followed by, I don't know, 20 zeros or more, and I mean, it's just actually make that 22 zeros. But there's just so many opportunities. There has to be intelligent life. But whether intelligent life exists near enough to us to do something about it, that one I don't know about. But I think it's definitely out there somewhere.
Thank you so much, Sara. This has been incredible. Really inspiring.
You're welcome, and great talking to all of you. I wish you all the best.